In this video, we're going to go through work, energy, and power. So a lot of this will be GCSE stuff, but it extends on that. And obviously the questions are much more demanding than GCSE, even if the formulas look similar. So we're going to start with the relationship between energy and force. So this is a really fundamental and important relationship. And work is done, or that's just another way of saying that energy is transferred when a force moves something. And it really is that simple. When work is done or energy is transferred when a force moves something, and it nicely relates work and force. So in mathematical terms, work done is force times distance, but we have to be a bit more specific than just saying this at A level. We have to say work done is force times distance moved in the direction of the force. So what this means is if we think about someone walking along the ground, have they done any work? Well, depends what you mean, really. Work against gravity, well, they haven't changed their height. Gravity obviously acts down. They haven't done any, so the work against gravity is 0. But they have obviously done work because it obviously has taken energy to move. So what might you describe this as? Well, you might say work done against friction. For example, to work out, how much energy it's taken to move or what force you need. Now, obviously, we are slightly simplifying it. Human body, obviously, you need work to lift your arms up against gravity. So if this person's arm is doing work against gravity, you obviously need to transfer energy for all your processes in your body. But we're obviously simplifying this just in terms of forces in physics. So work done is force times distance, but we know at A level that you might have a force at some angle to a surface, right? So maybe I'm moving this piece of wood, but my force is at an angle. So this becomes work done is FD cos theta, all right? So we want work done in the direction of the force. So this might not be a very clear example, what am I actually doing here? If we slightly modify this, so maybe I've got a box here and I want to move the box over this way here. Well, if I push the foot with a force up in this direction, here's me pushing with a force up here, then obviously some of that force is kind of wasted going up when we want to push it this way against friction. So clearly, we want this component of force here, and this component of force becomes the cos component, FD cos theta. So this is the first part of the lesson. Now, this might be expressed on a graph, force against distance. So we've got here's a constant force. Why is this important? Well, the area under the graph represents the work done. If we're talking about other objects, maybe like springs, which you look at the materials section, maybe the graph is something like this, where it's not a constant force, the force is changing. So again, the energy transferred is also the area under the graph. But here, this would obviously be FD. Here, we've obviously got half FD. So for a spring where we're changing the force as it extends, then the force is not constant. And so we need to use this equation, which you might recognize from GCSE. You might also have a situation where the force is changing, like this. Again, we've got the work done, and you might need to count squares to work this out. And we also need to recognise that there's a difference between the average force and the peak force. So in terms of, can an object withstand a particular force, we are obviously going to be looking at the peak force. If we have some object being dropped on a surface, is this going to break? Well, we need to look at the peak force. And if we can reduce the peak force, that's obviously a good thing. And we can do that by extending the time of collision, for example. What about if we're lifting something? So now we are doing work against gravity. We've lifted it some height. So again, work done is force times distance. What's the force in this case? It's gravity. We're doing work against gravity, therefore the force becomes the weight. So work done is this, or mgh, as you're used to seeing, all right, because we're talking about a height. What else do we need to know? Well, something that is used all the time and we've been using this year is kinetic energy. You may never have seen the derivation for this, so it's quite useful to show you. So we're going to start with a couple of equations that we've seen before. We're going to start with an equation of motion, right, which in the mechanics lessons we derived from very basic equations and graphs. We're also going to keep our definition of work done, force times distance, and we're also going to combine Newton's second law. So three really, quite basic equations that hopefully you're happy where they all come from. So firstly, we're going to substitute this one in here. So we're going to say work done is mass times acceleration times distance. And now I'm going to rearrange this, v squared minus u squared over 2a for distance. I'm also going to change this distance to an s, just so the distances are the same. Okay. Now I'm going to rearrange this. So I've got S is work done over mass times acceleration, and I'm going to substitute this into here. So I've got v squared minus u squared over 2a equals work done over mass times acceleration. I'm then going to rearrange for work done, which is mass times acceleration, and then v squared minus u squared over 2a. Let's expand out the brackets. Ma v squared over 2a minus ma u squared over 2a. The a's obviously cancel. So what have we got? We've got work done is half mv squared minus half mu squared. So we've proved that the work done, which is obviously the same as the energy transferred, is half mv squared minus half mu squared. So this is obviously the energy required to change the speed of an object. If the object is moving at a constant speed, then obviously there is no u. Right, we've just got the final velocity, so it simplifies to half mv squared. Right, a couple more small things to go over. Something else that is incredibly useful to use. If we start with work done is force times distance, and then what happens if we divide both sides by time? Well, work done over time, energy over time is power. Distance over time is velocity. Power is force times velocity. This is really useful in physics for certain situations, and it's also really useful in exam questions as well. And it often catches people out because people sometimes forget that this is a valid equation and that this is useful. And so a lot of people moan about certain exam questions, and you might have seen people talk about A-level exam questions in the past and some particularly nasty ones. And it's mainly because I think they've forgotten this relationship. And then there's one more relationship, which I think I have mentioned before, which I'm not going to derive again, but I will let you prove to yourself that this is a valid relationship. And again, in certain situations, this is very useful. It doesn't get used quite as much at A level, but occasionally it pops up. So it is really useful to remember that this is valid. And P here is momentum, whereas P here is power.